So if you remember from the video on Euler's number, E is like the natural growth rate. It seems to model growth or decay of populations or other things pretty well. That's why we use it. The reason why it seems to do so is kind of covered in that video, doubling and doubling and doubling again. That went through in the video. That kind of suits a population kind of model sort of thing. And that's why the inverse of E, natural log, ln, is called the natural log. Log base E is called the natural log for that reason. So there you go. So anyway, what I'm going to do is I'm just going to express this in a little bit of detail here, and then we're going to work our way through a couple of examples, and then you can get stuck into practicing yourself. So the base function, the way it tends to be written is A, so a function A, amount, is equal to an initial value, A sub 0, multiplied by E to the power of KT. Okay, that's how you would write it. So if you want to, you could write a little note to yourself saying that this A sub 0 is the initial value. So you'll see this in the examples that I go through in a second. So it's like saying, the population of kangaroos on an island was 7, blah, 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 blah. 7 is the initial value. Okay, so it's the starting value. E is the growth rate. And then we've got T, which normally represents time passed, whether it's seconds, minutes, hours, years, whatever else. So T is the time that's passed. And then K is this proportion value, which sort of affects whether it's growth or decay. So if K is greater than 0, guess what? It's a growth model. And if K is less than 0, then it's a decay model. Okay, so that's basically it. So if K is negative, then you're going to have, I might just do this on the whiteboard rather than on the screen, so just stating it for the video's sake. Okay, Charlie, all good? So if K was negative, like e to the negative 3t, say for example, then we just remember that a negative power means that it's the same as 1 over the power made positive. So can you kind of see that would be like a fraction, and therefore it's decaying, it's getting smaller and smaller. Whereas if K was positive, then it's going to be 2.7 roughly to the power of a positive number. It's going to get bigger and bigger and bigger. So growth if K is positive, and decay if K is negative. And often we might start off, and we're going to see this in the next problem, as we might even go for a decay problem, A equals A sub 0 e to the negative KT. So if we did that, then because we're explicitly stating the negative, for a decay problem, we would expect the K then to be some sort of positive number, okay, because we're making it negative. Am I making sense there? Okay, let's get stuck into some examples then. Oh, questions? Yeah. 1. Well, actually, can I, that's a good question. Put a pin on it for a second. I've obviously missed the value K equal to 0 as well, haven't I? Why? If K was equal to 0, ... Sorry? Well, no, because you'd be multiplying the time by 0, so that's fine. So if it was 10 years, say T equals 10, you'd have 0 times 10. So that's okay. Doesn't make the time equal to 0. Something else. Yeah, the whole thing would be equal to 1. Now, there's a complex term we use in algebra for that. So we would have A is equal to A0 e to the whatever K is. So if K is 0, it doesn't matter what T is, we'd have A e to the power of 0, if you like, 0 times T. which would just be equal to A0, right? Because E is just 1. E to the power of 0 is 1. Does that make sense? So if E to the power of 0 is 1, regardless of whether it's 1 year or 50 years or 1,000 years, that means however much time has passed, the amount is always just going to be the initial amount. And that's it. If I graphed it, it would look like this. There's T, there's A. This is great for the video, I reckon. There's T, there's A, and there's A0, whatever that value is. It would just be that. So the complex terminology we use to describe a situation when K equals T is that A, the function A, is boring. There's nothing to it. Okay, so we don't bother considering K equal to 0. Now, Tian's question is, why use a base of E? Now, you said, why not use a base of 1? Now, a base of 1 would also be boring, right? Because 1 to the power of whatever is just equal to 1. Yeah? So that's why I don't use 1. But why not use 10 or 12 or pi? And the answer is, well, it depends on the circumstance. Generally speaking, as I said at the start of the video, generally speaking, E, that value 2.717, blah, 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 tends to model population growth well. Okay? But in different circumstances, you may use a different base. If something is doubling every hour or something like that, you would use 2 as the rate instead of 2.7. If something tripled every hour or multiplied by 10 every hour, you would use 10 as the base instead of E. But because we're doing the kind of problems we're looking at are using E as its base because of its experimentally it has been shown that E models growth rates quite well. So the answer is that's why, but there's no reason why you couldn't use another base if you had a good reason to do so. Does that make sense? Yeah, I encourage you to watch that video again that I showed you when we started talking about E, the Euler's number in general. It's got to do with, it's a number that approaches when you start doubling every time period and then keep on slicing up the time periods into smaller and smaller time periods. It turns out that 2.7 becomes like this magical number, but it's in the video, so rewatch the video. Yeah, cool. Thank you, Tian. Really good questions there. Alrighty, I'm going to get on to looking at a couple of examples so you can get into it. These examples are from the textbook. That's why I said example 33. Please stop me as we go along. Gents, questions down the back? Anything at all is fine. Just get it clarified so that I can move on with the lesson. Nope. Would anyone like to remind Charlie why we're doing it now, even though we've just done the test? Because I did make it really clear at the time. Sorry? We've got internal exams, we've got external exams, and retests as well. This stuff is part of the course. So you have to know it. Okay? If you don't know it, you won't know how to do these kinds of problems, will you? Even if I knew that it wasn't going to be on any more tests this year, if it's part of the course, it is my duty to teach you how to do it. Fair question though, Charlie. After 1,000 years, a sample of radium-226 has decayed to 64.7% of its original mass. Find the half-life of radium-226. So the half-life, of course, is where the mass is at 50% of its original mass. It has decayed to 50%. Okay, so the key words there. Through the first read, I can see the word decay. So I know that I'm going to have to use a negative e to the power of a negative number. So I'm actually going to start with e to the negative kt as my thing. What else do I need to know? I need to know the initial value. Do I have the initial value? Not yet. I don't. I don't have the initial value. We'll see how to deal with that in a second. What do I have? Well, I know what's happening at 1,000 years. I know that it's 64.7 of its original mass. So its original mass is A sub 0, A0. And I know that after 1,000 years, it's going to be 64.7% of the original of A0. And then I know that I need to find the half-life, which is a half of A sub 0. Okay, so I know a bunch of things. So I'm going to model this as A is equal to A sub 0 e to the negative kt. That's going to be my model. And t is going to be in years. That makes sense. There's no need to change the units at all. So away I go. Slide 3, solution. At t equals 1,000, that's 1,000 years. What do I know? I know that A is equal to 0.647 of A sub 0. Does that make sense? 64.7% of A sub 0 is what I would be left with. I can't make it any simpler than that because I don't know what the initial mass was. I don't know what A sub 0 is. I don't know the initial amount. However, have a look at what happens next at my problem. Oh, question? No. Have a look at what happens next. Instead of A, I'm going to write 0.647A0. And on the right-hand side, I'm just going to write it as I had it, which is A0 e to the negative 1,000k. So just to explain that, because I've just rewritten it a bit, I've replaced t with 1,000. My k is at the end there because I put it there, and then I've just left the negative out the front. Okay, that's it's not a negative 1,000 years times k. It's 1,000 times negative k. I've just put it in order. That's all. Now, good news. I know that A0 is not equal to 0. It wasn't a 0 mass to start with. So I can divide both sides by A0, and that will eliminate A0, which is great because I want to have an equation with just one unknown. So I'm going to have 0.647 is equal to e to the negative 1,000k. Now that I've got it into e to the power of something equals a value, I can use my basic log definition to rearrange that to get to the k. Or if you want, you can think of it like I can take the ln of both sides and the ln of e to the negative 1,000k, the ln and e will cancel each other out. Either way, I'm going to get minus 1,000k is equal to the natural log of 0.647. Okay, now, in the second example, I'm going to show you a little bit of calculator work. But in this one, I'm just going to say that I've got the numbers already that you can use, but you could use your calculator for it. So negative 1,000k equals ln 0.647. So that means that k is equal to, now I've gone straight to the answer in my notes here, k is equal to ln 0.647 over negative 1,000. Okay, so you literally are going to put that into your calculator and you will get 0.000435 to 3 significant figures. So I've now got a value for k. I need that value for k because without it, I can't work out the half-life effectively. Question? You sure? Anyone else? I'm not done yet. This is just the setup. Okay, so the half-life is at a half A0. Okay? So half-life is going to be when I've got half of the original amount left. So now I can use half A0 in my equation. So I'm going to go a half A sub 0 is equal to A sub 0 multiplied by e to the negative kt. Divide both sides by A sub 0. That gets rid of it. And I'm just going to change a half to a 0.5 because that's more, it makes more sense for this. So I'm going to have negative, so 0.5 equals e to the negative kt. We've got our value for k. I'm just putting k in because I don't want to put in that big nasty decimal number in. On your calculators, you should use whatever your calculator tells you. So now I'm going to use my basic log definition to make minus kt, the power of e, equal to ln of 0.5. And then I'm going to divide both sides by negative k, so negative 0.00435. So divide both sides by negative k, and I end up with 1591.95. Job done, right? Not quite. We need to answer the question. With these sorts of questions, it's always worth making sure that you've answered it. It says find the half-life of radium-226. I think 1591.95 is a reasonable number for T. But I'm going to be very clear, and I'm going to say IE, that is approximately 1,592 years. Done. So what I've done there in the final line is I've just put my units in. And in an application problem, if you don't finish with the units in, whether it's years or whatever, then you've missed a trick. K is unitless, by the way, but you need to finish off with making sure that your statement agrees with what it's been asked for. Deepam? For context, really. I'm glad you asked that because it's going to come up over and over and over again, and there's no one size fits all. You need to look at the context of the question. You need to say, well, if I'm talking in thousands of years, or hundreds maybe, I suppose, but it's now in the thousands, then whether it's, you don't need to say, well, it's going to be, just to take it to a ridiculous extent, 1,591 years sometime in December. Do you know what I mean? You don't have to be that specific. It contextually, you'd be going, well, the size of years we're talking about to the nearest year would be absolutely reasonable in the context. If you wrote 1591.95, in this particular context, I wouldn't mind so much, but I think it shows a deeper appreciation, understanding of the numbers you're dealing with by rounding it to the nearest year. Does that kind of make sense? Yeah. Any questions? Okay, I have a second example to show you. This is a decay problem. The next example is a growth problem. It's got different things going on, so I want to show you that as well. But I also want to show you the graphics display calculator usage as well. So I'm going to stop this video and start up a new video because I can't switch screens with the video I've got now. So while I'm doing that, if you just want to have a quick stand-up break if you wanted to reset your brain, and then we'll start again in about 50 seconds, I reckon.